you will be doing some sort of Lyapunov equations and other control stuff for your project. So, and I know that it's kind of difficult to explain all of the theoretical background material in a short 15 minutes lecture, 20 minutes lecture. Probably we'll have about like 15, 20 minutes, including questions, because we have practically 6 projects. And the 6 projects, we have 1 week of lectures, which will be about 3 hours or something like that. So you need to fit into that 1 hour, you need to fit 3 lectures, something like that. Plus maybe a little bit of questions, some spare time. So my plan is that you will have lecture of about 15, 20 minutes. This is how I look at it. And then you have probably like 15, 20 slides total. And explaining all control theory in 15, 20 slides is not feasible. To understand where you're going with all kind of controllers and that kind of stuff. So I'm thinking just to give right now prerequisite for people who are not in controls area to understand at least what state space is, what stability is, why we care, and things of that kind. Maybe talking a little bit about Lyapunov and equations, but not too much. So I will leave it to you to work on the controls part, all right? Any questions on that? And now semester becomes a little bit more interesting in the sense that now I need to pick and choose different kind of topics, because we have probably like 1 million topics left uncovered, and we have only a few weeks left. So we need to choose something which might be more practical for your particular applications. So if you have, and here's the plan. So I'm thinking to talk first of all about very important topic of convergence and invertibility of matrices and sensitivity to solutions and numerical stability, numerical convergence. So Stephanie talked a little bit about some sort of round of errors and that kind of stuff previous lecture. So I want to expand that to other topics related to linear algebra, because these topics are very important. Many times you get all kind of problems and errors because you do not pay attention to condition number of the matrices, to all kind of other important things about matrices, and you try to invert something which is almost not invertible, and then you get wrong results or not very close results to reality. And you need to understand like when you can do that and when you cannot do that, right? So this is the idea, just to have your assumptions right. So this is number one that I want to talk about. Number two that I want to talk about how to solve nonlinear equations in general. To have some sort of nonlinear equation, you want to find roots of that equation. Sometimes you want to find minimal, maximal of these equations, which is optimization problems. So I want to talk a little bit about optimization and finding roots of different nonlinear equations numerically using algorithms of some kind. And third thing that I want to talk about is interpolation or extrapolation, which means you want some function to pass through the points, given set of points, not like least squares approximately, but exactly. But I want to find values between these points, which means like what it should be between the points. And there is always infinite number of possible solutions, because there could be anything between these points. But you have all kind of constraints that you put on that. It needs to be linearly connected, or it should be smooth, or it should have like 3 derivatives which are continuous, or it should be, you give it particular property, or it should be polynomial. You have all kind of properties that you can impose on the points between the given points. And then you do interpolation of different kinds. So we can learn about interpolation. And these problems are extremely practical because typically you want to know what happens between the points when you have some sample data. You want to model it, like what happens, like you want some continuous function passing through these points instead of discrete points. But you can tell me maybe something which is useful for your future research or something numerical that you plan to do or doing already, which we might want to cover as well, just that it will be more practical, more useful, all right? Any questions on that? Okay. Yes.
Can we do maybe a lecture on information theory? Oh, that does not.
Oh, information theory. Very interesting topic. Very long topic. But even if I will start lecture on entropy and computation of
General capacity.
capacity and all these things, it will take me probably at least a few weeks. So I'm talking about like, can we cover something within like 1 hour? It's that kind of add on to whatever we've done before, not completely new
Topic.
But this is very interesting topic. Just
I guess too much
outside
outside
of the scope
within
in the time limits that we have.
All right. So
We are talking today about dynamic systems. And dynamical systems is practically everything which has inputs and outputs of some kind.
which means it could be
Engine, it could be our brain, it could be
all kind of
microcontrollers, it could be
audio amplifier, it could be all kind of things. Stock market, you have all kind of examples here, but practically it's anything that has inputs and outputs. Now, why we do not want to call something without input and output a system? Because if you don't have any output, you have nothing to measure, so you don't see any result from that pseudo system. Okay, so we don't really care analyzing that type of systems where we cannot measure any output. They're invisible systems in a sense, so we don't care about that kind of systems. And if you don't have any input, then you cannot do anything with that system. Okay, the input still could be hidden inputs, but you need to have some inputs. Because if system has no inputs, you cannot control it, you cannot do anything with that system. It kind of runs by itself and you have no access to it whatsoever. So it's not that interesting for engineers to have that kind of systems. So what we'll be covering only systems with inputs and outputs, right? And I will talk only about single input, single output system for simplicity, but you can have multiple input and multiple output type of systems. Same thing in state space, you'll have multiple inputs, multiple outputs. So if you took any engineering courses, you don't have to know any details of that. If you haven't learned about differential equations, that's fine. Just skip that part. Sound like blah, 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 whatever. That's okay. This is just example that most of the continuous time systems could be described using some sort of differential equation. Differential equation in general could be written as some sort of y, which is output of the system, is a function f, and this could be any linear or nonlinear function of all kind of derivatives of y, and also inputs u and their derivatives as well. Okay, so it's like combination of all kind of input-output derivatives and inputs and outputs. Okay, it could also include all of the previous inputs and outputs. Could be all kind of things. Okay, depends what the thing is. So pay attention that I included y here, which is kind of not exactly right way to write that type of equation. So you have y on the outside, and you have also y inside of that function. Okay.
So y is a function of itself, in a sense, recursively.
Now, typically, if you go to any textbook about differential equations,
and they need to define some generic differential equations, they define that in implicit form, which means f of all kind of things equals to 0.
All right, this is
Typical differential equation, generic differential equation. So I want that y to be here just because I want to talk mainly about discrete time systems. And in discrete time systems, you'll have equation of y of k, index k now, k would be like 1, 2, 3, 4, 5, sample k.
Function of all of the y's, including the particular thing. So it's kind of function of itself, all of the past samples. So why I always can write it that way mathematically? What do you think? Why first equation
is still okay. I mean, you will not see that properly in textbooks, but I can do that always.
It's still correct.
You mean
Why any f of anything equals to 0, I can write as y equals to f of
Everything else. Why?
as a completely equivalent form.
By Taylor series?
I'm sorry,
Taylor series.
zeros?
Taylor series.
Taylor series?
Is Taylor series
Mm,
say
this is not,
everything?
no, I'm not using a Taylor series. This is simple algebraic trick here.
Nothing from calculus.
This is actually much simpler than that.
Why any equation which you can write as f of something equals to 0, you can also write that as f of something equals to y, or any other variable, or anything practically. Anything which is built from the variables which are inside of that function.
So what I'm saying is practically something like that. I'm saying you have some function alpha, beta, gamma, variables, whatever they are, could be derivatives, could be variables, could be whatever. I'm saying this is my original function. And now I'm saying, well, I can say that this is the same thing as some other function of alpha, beta, gamma, and so on equals some other function of alpha, beta, gamma, so on. So these two are completely equivalent. Which means I always can find f1 and f2, that this thing will be completely equivalent to that thing.
They say they share the same element. The
What
alpha, beta, gamma, they same, so you can always.
Can you tell me what f is?
Because the first function can be written as linear combination of.
No, it's not linear combination. It's some non-linear function. It could be like alpha squared plus beta cubed divided by logarithm of gamma, and all kind of things. Something non-linear, complicated. So why these two are the same thing?
They're the same form.
So you can get from this form, you can get to that form, and from that form, you can get to that form. How? That's the question. Well, everything's written on the board already for you to know how.
And just like subtract the f2, right? f1 subtract f2.
This is just basic algebra. This is f1 minus f2. You just define your function f if you have that kind of thing. Define your function f as this one minus this one, and then you will get 0 by definition. Okay, or you can add both sides constant of some kind, some other function. So you can do here plus f1, and here it will be plus f2, right? Or you can add same function on both sides practically. It will not change anything, but this could be included inside because it has same variables, right? So you can modify that function in such a way that this will be jumping inside that thing. It will be different function, but still function equals to that f1, whatever it is. Because I just added both sides, same thing. It's algebra. Any questions on that? So this is the overall idea that I can always write the differential equation in that form.
And my discrete type of difference equation will look like that equation, okay? Obviously, also need initial conditions for any differential equation or difference equations you need, where you need to start with your initial y's, what is your uk vector, and practically in textbooks, again, sometimes people put it as subscript instead of time. So k index is an index of time, and it is integer number, 1, 2, 3, 4, 5. So you get y of 1 equals some function of y of 0, y of -1, until you get to y of 0. But so you need to start with some point which is k larger than that number of delays that you have here, okay? Otherwise, you need a lot of initial conditions in the past, in the negative time, right? Okay. Oops. So let's see some example.
And again, if you don't know Z transform and all that stuff,
just ignore.
Ignore that. Believe me that the inverse is delayed by one sample. Okay.
And when you're building all kind of systems in discrete time, you can draw it as block diagram with all kind of delays. So taking your input u of k, you're delaying it by one sample, you get uk minus 1. Then you're delaying it by one more sample, you get uk minus 2, and so on, until you get, for example, to y of k, which is also having multiplication by 3 here, and adder here, multiplication by 2, added here. So this is some sort of system. Okay, you can have all kind of systems. We'll write that equation in a second for that particular system, just to see how that stuff works. Okay. But before that, I want to define state variables. And okay, so the idea is that okay, so the idea is that we want to describe the system instead of single equation with multiple equations. And this is state space. If you learn differential equations in general, I don't know if you actually learned that, because
I learned that when I learned differential equations, but apparently people learn it in very different ways.
so we learned some sort of mathematical trick, which is saying that any differential
Equation
equation
of nth order, linear differential equation, all right? Regular differential equation, regular linear differential equations with some of you
could be always written as n equations of the first order. All right. So any differential equation of nth order could be written as n system of n equations of first order. All right. And you have some tricks how you get from one form to another form. Practically, the second form of the system of equations is state space. So here's how it looks like. Let's see. Interesting. Yeah. So what we have here, let's say some sort of differential equation, it will look like, I don't know, y 2 dots plus 5y dot plus 6y, all right, equals something like that. Some differential equation. Each one dot means derivative with respect to time. Okay, so each one of them is obviously a function of time. So these are inputs to your system. These are outputs to your system and their derivatives. So you have some differential equation of second order clearly. You can always write that system as two equations. And first equation will be of first order, which means only single dot. And second equation will be of the first order, which means only single dot. But these variables will be different and we will call them x. Okay, state variables. This is very different from the x's that we used in linear algebra, right? Kind of. We will still get to the same vector x eventually, but this will be different. So we'll have x1 dot and x2 dot equals, and first one will be function of x1, x2, and u. This will be some other function of x1, x2, and u. Right? So the idea is that you will always be able to write that kind of equation as system of two equations, but first order. And solution to that system is much simpler. And here's where you can use linear algebra, actually. Okay. And this is called state space, representation of the system. So this is just waving my hands, but let's define that more specifically, like what it all means. So what happens in physical systems, you define all kinds of parameters that you're interested in, and these parameters, are called state variables.
So state variables are all the parameters of your system that completely describe your system as a minimal set of parameters that will completely describe the dynamics of your system. Okay, so everything you want to know about the system at any given time should be described by your state space variables. It could be currents, voltages, velocities, locations, and other things that you need to know about your system. Those are called state variables. So after you define the state variables, and it's actually tricky how you define the state variables that you'll be able to write state space equations later. Okay, this is kind of separate theory that I'm not getting into. But after you define the state variables, which are completely describing your system, you can always transfer from the differential equation to set of differential equations of first order, and you will get n of them, and n is order of the original system. Okay, so far, again, I'm not talking about details, yes.
Is the state variables depends on the input or it's
No.
independent?
No, input is completely separate from state variables. State variables are describing the state of the system, not the input. Input is separate. You keep input as is. Okay. And we also will call state space the state. You could have like x1, x2, x3, x4, whatever number of states you have, and they could have some subspace in overall space of all possibilities, which is Rn, right? So you can have practically coordinates of that vector x1, x2, x3 as a function of time. And this trajectory is moving somehow in time given your inputs. So what happens is, since x1, x2, x3, and so on, they describe completely your system, you can draw the trajectory in n-dimensional space, how it moves as a function of time and input. So you're giving it some inputs, this trajectory, this axis are changing somehow, so you have that single point, so you think about x as vector now, okay? This vector is changing somehow as a function of time. So this is vector of time. And that's why the systems are dynamical systems, because they are changing as a function of time. Now, as I mentioned, you have that mathematical trick, which is always allowing you to convert one type into another type. So any linear differential equation could be converted into that kind of system of equations. Now, why are we talking typically about linear differential equations in general and also time invariant systems? So it's like LTI system. Again, if you have electrical engineering background, you heard about LTI name, linear time invariant systems. And this is like all courses in controls, all courses in signals and systems, practically all talk about LTI systems alone, nothing else. Practically, probably like 99% of this course is devoted to LTI systems. Why LTI? So first of all, what is linear system? So linear system is system like with linear algebra. Same thing, same idea. You have two properties which are telling you linearity of something. Property of homogeneity and superposition. And these properties are, if you have some system and you have some input and you measure some output. If you multiply that input by a constant, let's say 5, your output will be multiplied by the same constant. So this is homogeneity of linear approach, okay? So if you multiply input by something, the output will be multiplied by the same gain. Practically speaking, that's linearity, part of linearity. Second thing is superposition. Let's say you have two different inputs, whatever they are. So you put in one input, you get one output. You get second input, you get second output. Now, if you put in some of the inputs, the output will be sum of these outputs. This is superposition principle, okay, for all linear systems. So if system satisfies these two properties, the system is linear system, okay? What is time invariant system? Time invariant system means that you can shift origin of time to any point and the system will behave exactly the same way, starting from the original time point. So it doesn't matter if you started with yesterday or today, it will behave the same way, okay? Time variant systems will behave differently at different time points. So if you think about brain, for example, it's clearly time variant system because today we will respond differently from yesterday, okay? We have some mechanisms to have memory, okay, on what happened in that day. So we will be talking mainly about linear time invariant systems because this is what dynamical systems we are talking about.
state representations are. And the state variables do not always have to be any physical entities like current or voltage. It could be some sort of combination of them together, with some algebraic manipulation on them. There are multiplications or some other function of them, just for simplicity of representation, okay? And you also have infinite number of possible representations in state space, which means this is not the only pair of equations that describes that upper function. You could have infinite number of state space equations which are describing same differential equation. Now, these representations are completely equivalent. And if you're familiar with transfer function representation, for that differential equation, you clearly can find transfer function, which would be, can you say what transfer function of the differential equation is? So it will be 7s plus 3 divided by s squared plus 5s plus 6, right? I'm just taking coefficients of the right side and multiplying that as coefficients of polynomial of first order divided by polynomial of second order, because in Laplace transform, derivative means multiplication by s. Okay, so it will be like s squared from the two dots times 1, which is coefficient of the s squared, plus 5 coefficient times s times y. So y will drop in the transfer function and so on. So you can find the transfer function of that differential equation as well. So this is the third type of representation for the dynamical model. Is it equivalent to state space and differential equation? What do you think? Is transfer function representation of functions in general equivalent to ODE, or differential equation representation of that same thing? Because I can clearly go back and forth from differential equation to transfer function back, right?
Because you have to, because it depends on your initial condition.
Exactly. So what are the initial conditions for transfer functions? Any of them.
The initial,
So for transfer function, do you have any initial conditions? So what are they? No. For differential equation, you have additional conditions, right? So you have, in that case, you also need to give here additional thing, which is y0 and y dot 0, let's say, or any other point, whatever, initial conditions, okay? So without that, you cannot start even solving that, right? Because you don't know what is the initial point where you start all these things. Same thing here, you need to know like what is x1 0 and what is x2 0. Without that, you cannot start iterating on that, because this x1 dependent on x1, which would be kind of previous in time, 1, right? So without knowing the previous one, you cannot start iterating on that. Same thing here, but not with transfer function, because transfer function will be that thing. In that case, it will be 7s plus 3. Here I'll have s squared plus 5s plus 6. People even cannot put any initial condition on that stuff. So what is the assumption on the initial conditions for that kind of transfer function? When you're saying this is my system.
initial condition or 0.
Exactly. For all transfer functions, initial conditions are 0 by definition. It means it's 0 state response. Transfer functions are 0 state response. All right. And this is not 0 state response. This could be 1 and this could be 5. Okay. You have completely different solution to this too. If you draw y as a function of t for that thing starting not from zeros, you will get very different response from if you draw in output here, because it's by definition 0 initial conditions. You will start always with point 0 and then y will change somehow. Okay, so completely ignore response to initial conditions. You're just assuming
that you can ignore it with transfer functions, which is typically not really correct. Just easy, but not correct. Okay? So they are not equivalent. And what happens is that transfer functions do not have initial conditions, or they have initial conditions 0 by definition. And ordinary differential equations and state space equations, they have initial conditions. They are more generic. Okay. Now, what are the advantages of having that state space representation in general? So that's what we discussed already, is that it's equivalent to ODE and it has initial conditions and not like transfer functions. You have practically uniform controller design and analysis to MIMO systems, multiple input, multiple output systems. It's just matrices that describe the state equations become different dimensions, okay? But all of the formulas, all of the ideas, all the derivations are practically the same for CISO, CIMO, MISO, MIMO, all of the systems with multiple inputs, multiple outputs, and so on, right? So it's almost uniform analysis for continuous time and discrete time systems. Again, instead of state space of x dot equals ax, you will have x of k plus 1 equals axk. So you'll just call the vectors differently. You'll have like discrete samples instead of continuous time functions, but matrices will be the same, all right, in the linear representation. So treatment of the series will be exactly the same practically for discrete time and continuous time variables. The only difference will be stability of these matrices, stability of the systems. Because stability in discrete time will be all of the eigenvalues of our matrices will need to be in the unit circle. And for continuous time, they will need to be in the left semiplane. This is the practical difference between the two, but everything else is practically very similar, right? Very similar type of analysis. And again, if you don't know about what we are doing in control theory, we are putting poles in all kinds of places to control the system, to get all kinds of characteristics of the system to make it work and provide performance of some kind, like settling time, overshoot, steady state error, and other things. Again, you can ignore all of that if you are not in controls area. But you can control it using location of poles. And poles of the system are practically eigenvalues of that state space matrix that I will show in a second. Okay. So it's all interrelated and interconnected using our theories that we already learned in that course on eigenvalues. Optimal controllers and optimal control in general, all based on state space. And this is what people typically use in all of the applications, control theory. Nobody is using any more classical control except maybe PID controller, which is still very popular in all kinds of applications, like integral, derivative, and proportional, which is PID. But other than that, everybody is using LQR controller, which is optimal controller, LQG controller, which is also optimal controller, Kalman filters, which are optimal observers. All of them are based on state space. So if you want to learn about that, next semester we have course on modern control. It's all about all of these topics, okay? It's all about observers, controllers, how you design in state space. So I'll go into details because right now I'm trying kind of to cover half semester of a course in one short lecture of less than an hour, right? But I will be much more detailed in my presentation of modern control in the next course, next semester, okay? It's called Modern Control Theory. And also you can expand that to nonlinear analysis. So instead of having matrices, you can have some functions of matrices and variables, access, in all kinds of things, and you can analyze it in state space instead of analyzing that as nonlinear differential equation, which typically is much more complicated because analyzing equations on first order, it's obviously more easy than analyzing equations of nth order differential equations, right? They're still nonlinear, but I guess the first order is nicer because
right, so here's how it looks like in discrete LTI systems, right? Let's say you have that difference equation, yk plus some coefficient times yk minus 1. This is all of the y delayed up to 0 time, all right? And same thing with the u. So have inputs at different time points from 0 to m, and all kind of coefficients. So you get linear combination of them practically here and linear combination of them there. All right, that's what you get. So you can write that for each point, okay, as state space variables. So you get x1 of k plus 1 equals some coefficient times previous k, another coefficient times previous k x2, and so on until you get to the last one. And if order of the system is n, or in that case, n, so the system will be n by n. Okay, so we'll have n by n coefficients here, which also could be written as a matrix times some sort of vector. And at that point, I'm not even explaining right now. Again, next course, I will explain how you get from this one to this one. Like what is the relation between the coefficients alpha and beta to coefficients A in the matrix. But you always can write it that way. You have standard ways of doing that, how you convert that difference equation to that equation, all right? And this is for 0 input u, like all of these coefficients are, all of the u are 0 for that case. So you have practical equations that you saw before. Remember that equation where we saw that before? So the next x vector equals some matrix times previous vector x, which is exactly that same, that's in matrix form. Where did you see it? This is not exactly A equals to B. It is, I mean, kind of. It is A equals to B, but B equals the previous x. So this is iterative. You iterate with k equals 1, 2, 3, 4, so on. You iterate, and you get practically like what is the solution of that thing. It's a to the power of k times the x0, right? So if you're starting with some initial conditions on x, and then next x will be a times x, next one will be a times x, then a times a times a. So it's like powers of a times x will be the solution at point k. This is explicit solution. This is implicit solution, and you have explicit solution, which is a to the power of k times x, 0. So what is that thing? You saw that before, okay?
Trying to find the biggest eigenvalue through that.
This is how you found dominant eigenvalue power methods, okay, powers of A methods. This is exactly what the state space is doing, okay? It's kind of trying to converge to a particular eigenvector, which is dominant one, and it will try to align itself with a dominant eigenvector. So now you know what it means, okay? People in controls do not learn it that way. They do not think about these connections to eigenvalues and eigenvectors, but I'm showing connection to eigenvalues and eigenvectors through something else, which is actually related to transfer functions. Because for that particular function, if you're taking eigenvalues of that matrix A, the square matrix, n by n square matrix, to get n eigenvalues, and they are solutions of characteristic polynomial of that matrix A. So this characteristic polynomial is polynomial of poles, which is in that case on the board is s squared plus 5s plus 6. So for that matrix A, eigenvalues will be roots of that polynomial, which is very unexpected and interesting relation. So eigenvalues of the system are poles of the system practically. They are equivalent, same thing. And they are solutions of the transfer function bottom polynomial denominator, right? So here is a state space representation. Now, if you have also input, you can add to that vector of b, b1, b2, all of these are constants, times input u, okay? So the overall state space system will look linear state space system at least. It will look like next x equals ax plus bu. This is standard form of all state space systems. Now, the output will also be written as linear combination of x. So it will be some matrix C times vector x plus matrix or scalar in that sense for CSU systems times input u. So this will be y, which is output of your system. And this will be two equations, which are standard two equations for state space representation. It will be next x equals ax plus bu and y equals cx plus bu. All right. Typically, d equals to 0 for strictly proper systems where number of zeros is less than number of poles, but d will not be 0 if your number of zeros equal to number of poles, okay, in that representation. And all of them, as you see, all of that is sampled. So all of this A, B, C, D matrices are constant matrices. All right, so far. So this is how you describe the system. And now we will have to write that specific example, okay? So we will try to write state space equations when I already defined for you what are the x's that I want to choose. And I will choose this point for x1, this one for x2, and this point for x3, okay? And I want to write that difference equation, which is describing that entire system, as system of difference equations of first order. Is it clear what I'm trying to do in that exercise? Okay.
Okay, let's see how it goes. Again, if somebody defined for you the state, okay, all of the x1, x2, x3, in terms of the other derivatives of u and y, this is relatively easy exercise. But the difficult part is how you decide what is x1, what is x2, and so on. So typically we put all of the x's at the end of the delay blocks. Okay, this is standard way of dealing with things. And everywhere you have delay block in your overall system, output of that will be x. And you need for each block, you need one x. All right, so number of delay blocks will define how many x's you have actually. Number of blocks will always be equal to the order of the system. All right, so let's see how it goes. So I will draw the system first that you have that for reference. U, A, belongs to some sort of one delay, second delay, third delay. Then line that one by 2. Gain of 2 goes to adder. This one is multiplied by gain of 3. Adder. This is y of k. We define that one as x3 of k, x2 k, x1 of k. So pay attention that if I would change the order of x's, this will give me completely different state space representation of the same system. It doesn't matter how I call this one. Is this one like 1 or 3? Right? I can switch order of x's in any way I want. It will give you different representations of different A matrix, all right? But it still will be legit representation of the same system, which means it will have same transfer function, same difference equation, same other properties, same poles, same zeros, same everything, all right? So it doesn't matter how I call it. And this is why you have practically infinite number of possibilities here, how you define x's. But if you define them kind of unwisely, then you will not be able to write this system of equations, okay? It will not kind of match somewhere. And this is a tricky part, like how do you know how to choose it in some wise way, all right? And you have standard ways to do that. Okay, so you have, that's right equations that we have so far. Just by looking at the diagram, what I have is x1 k. Pay attention that I want to write it as x k plus 1 equals a x k plus bu. Okay, y k equals z x k plus du. Right, that's what I want. which means that all of the x's need to be dependent only on previous x's. That's it. I don't want to have any y's in here. I want to have only x's and only u. This is what I want. Okay, so let's see, what is x1? So x1, practically this one delayed by 1, right? So it's x2 delayed by 1. Yeah, z inverse means one sample delay in z transform. When you multiply by z inverse, you delay the signal by 1. So you're taking this one, delaying it by 1, you get x1. So x1 equals this one delayed by 1. Same thing with the second one. So x2k is x3 delayed by 1. Okay. This one is this one delayed. x3k is what delayed by 1? Delayed by 1. Okay. What else we can say about y? So what is y? Also want to write it as a function of x's and u somehow. So what is that? That is x1k that's from here. So adding x1k plus 3x2k plus 2 x3k. That's it. Right? Okay, so far. So just looking at the diagram, writing these equations. Now I want to write that in that form. Okay, so that form will look like that. I want x on k plus 1 plus 1. Something is a function of other x's. So what it will be? So if you add here 1 and add here 1, you'll have x2k. You just shift everything by 1. Right? So x2 k plus 1 will be x3k. x3k plus 1 will be uk. And yk we wrote already. That's already in the form we want. So now I want to write it as matrix times vector, right? So what from here, what I want to write is x1, k plus 1, x2, k plus 1. This is the vector x. x3, k plus 1 equals some matrix. What will be the size of that matrix? Times again vector x1k, x2k, x3k. What are the dimensions of that matrix? 3 by 3.
Yeah.
We have 9 values to put here. You want that thing to be equivalent to that thing plus b times, oh, let's see that on the boards, we'll plus matrix b times uk. The overall system, right? So what is that element? So what multiplies x1 in that equation? So x1 k plus 1 equals something times x1, something times x2, plus something times x3. So what is the first thing? What
Zero,
multiplies
0, 1, 0.
0, 1, 0. Nothing multiplies x3 and x1. 1 multiplies x2. How about the second one?
1, 1, 0. 0, 1.
0, 0, 1. How about the third one? Tricky one.
0, 0, 0, but
All of them are zeros. You have the u part. So what multiplies u in the first equation? 0, nothing. How about second one?
0. And then
Nothing. How about third one?
1.
1. Done. That one. Okay. So this is the first state space equation, which is saying this is my matrix A, this is my matrix B, and now I need Y to be something times xk, 1, 2k, 3k, plus something times uk. So first of all, do you have any uk in the y equation? So this will be 0. Don't need that part. Okay, so d equals to 0. What about this C matrix, which is in that case vector because it's a CISO system, single input. Will be row vector.
3 and 2.
You have 1,
3.
3, and 2. That's it. These are state space equations for that particular system. So we wrote that as next x equals some matrix times previous x plus something like vector b multiplied by input, and output of the system is some vector multiplied by x. That's it. This is the representation of the thing. All right? Any questions on that? Okay. And this is MATLAB code. I can share it. Okay, this is just example of how you iterate on state space systems and how the trajectories might look like. So if you define this vector x, which is initial conditions as 10, 15, this would be the point here, okay, the star point as a trajectory. And let's say you have some matrix A. This trajectory is easier to draw than that example because otherwise I need to draw it in 3-dimensional space. So this is 3-dimensional example. You can pick any other example here. You initiate in that state and you iterating, for example, 100 steps, which means you're drawing 100 step points for that thing. All you do is x equals ax, all right? With any, you can add to that also bu if you have any input. In that case, I don't have any input. So it's response to initial conditions. So starting with initial conditions, and you are trying to go with these points, iterating on these points. So your state will be that x that you are measuring each time. And then this plot is drawing the trajectory of that convergence. So pay attention that this system is stable. Why it is stable? Because it is converging to 0 eventually. It's asymptotically stable. It converges from initial conditions to that point. So if linear system is converging from any initial conditions to state 0, it is asymptotically stable and it will converge from any initial conditions, which is very nice property of only LTI systems, okay? Other systems might not. Other systems might depend on initial conditions. So sometimes it's converging, sometimes it's not converging. For LTI systems, if it is converging from one set of example, it converges always for all sets of examples, for any set of initial conditions, okay? That will converge here. Now, with inputs, it could go anywhere. It doesn't have to converge. But without input, it has to converge to 0 if it is stable. So this is what it means to be asymptotically stable. You have other kinds of stability. And one kind of stability is BIBO stability. And again, you don't need to know much details about that. It's bounded input, bounded output stability. where your input is bounded, your output needs to be bounded. Then the system is called stable. Right, this is people stable. And then you'll have also Lyapunov stability, which is a little bit different. It means that the energy is not introduced into your system, which means the system does not run away too far away from its initial conditions. This is the overall point of Lyapunov stability, okay? Maybe I will talk a little bit about that next time, but this is the overall idea, okay? The idea of state space, if you remember, it was something very similar that we discovered already in power law when we computed dominant eigenvectors. And this is that next state equals some matrix times the previous state. And you can iterate on that as many times as you want. And this generates some trajectory of x's in n-dimensional space. And this is example of two-dimensional space where you actually can draw the trajectory of x1 and x2, right, in space as a function of some sort of time component. And this time component, in that case of discrete time systems, is just index. So it's not that complicated, but in general sense, it could be any t variable, so it could be any time. So you can do that continuously when x dot equals ax. So this is matrix differential equation now, where you have derivative of x equals some matrix or change in x, practically that's what derivative is, equals matrix times vector at present state. All right, and then you can also draw some trajectories which will be continuous and not discrete anymore. So these trajectories that you see on that screen are actually just dots. For a particular k, you get single dot. So it's not continuous trajectory. It looks like continuous because I connected the dots together. But the actual trajectory is just a bunch of dots, right? So at each time point k, you have particular dot. All right, so far. So this was the example. Okay, now we move a little bit to different space, which will prepare you to have background to understand Lyapunov equations and things of that kind. So for that, we need to know what are positive definite matrices. And to define positive definite matrices, we need to define quadratic forms. As you may be seen in linear algebra courses. Have you seen quadratic forms before? Or saw quadratic forms before? Okay, so only a few of you saw in probably some linear algebra or other courses quadratic forms, which is relatively rare topic for linear algebra. For whatever reason, it's not difficult topic, nothing too complicated. And you see these quadratic forms almost everywhere in optimization, in controls, in multiple other domains. So quadratic form is defined for matrix A, which is symmetrical matrix A. You define quadratic form as x transpose AX. Okay, so you're taking any generic vector x, making transpose, which will make the vectors that way, okay, multiplying it by matrix, which is square and symmetrical matrix A, and then multiplying by the same vector on the other side. And, well, this is what quadratic form is. Now, pay attention that this definition works for symmetrical matrices, okay? So this is how it's technically defined. Sometimes people apply it to non-symmetrical matrices, and they try some properties on non-symmetrical matrices. It's kind of different thing, all right? So by definition, it starts with symmetrical matrix A, and it's important for our future things. Now, pay attention, what is the dimension of that type of expression? So it's vector times matrix times vector. So it's 1 by n times n by n times n by 1. So what would be the overall dimensions of that multiplication? 1 by 1. Okay, so it will be just number of some kind, okay? But if x is some function of time or some function of k or t, whatever it is, it also will be just a function, 1 by 1 function of one dimension of that time, all right? This is the overall idea. So if you have multiple components like x1, x2, x3, or here I call it x and y, but it doesn't matter, quadratic form of that thing will be some quadratic expression for two-dimensional matrix, which is 2 by 2 matrix,
or higher dimensional kind of multinomial of these variables of some kind, right? It will be just single dimension. So here's one example. Let's say you have matrix A, which is 3, 1, 1, 2. So that quadratic form of that will be just 3 times x squared plus 2 times y squared plus 2 times xy. That's it. This is a quadratic form. Now, this quadratic form could be positive, but not always. Okay, it depends on x and y. We typically will look for positive quadratic forms. So we will look for expressions which will be always positive for any x and y or any x1, 2, 3. Okay, this is what will be of interest to us. And this will, I will define that in a second, it will be positive definiteness property related to quadratic forms. So practically in geometry, if you're thinking about geometry, and again, geometry, we can think only about like 2 dimensions or 3 dimensions. We cannot imagine it in higher dimensions. But if you take like 2 by 2 matrix, all right? This formula, if you're thinking about axes like x and y axis, so what is that formula? What kind of function is that? What kind of shapes you can get with that formula? Like if you're plotting x as a function of y using that formula. So like level sets of that thing, which means let's say this thing equals like 3x squared plus 2y squared plus 2xy equals to 0 or any other constant. What is that shape? You have the answers here. Okay, so you can get parabolic shapes, hyperbolic shapes, or elliptical shapes or circles of some kind, ellipses. Depends on the coefficients that you have here, okay? So these are all of the quadratic, this is why it's called quadratic form, because these are quadratic shapes, like second order shapes, like parabolas and ellipses. For ellipses, like for circle, do you remember equation of circle? So what is the equation of circle, of radius r? Let's say with point at origin, like middle point in the origin. What is the circle equation? The simplest one. Unit circle. What is the equation of unit circle? Radius is 1 unit circle. Yeah, so the equation of regular circle, which is centered at the origin, is x squared plus y squared equals r squared, radius squared. Okay, if you want to shift it from the origin to some x0 and y0 point, okay, the center will be x0, y0. You'll have x minus x0 squared together plus y minus y0 all squared equals r squared. This is equation. And this still will be same kind of equation, right? You still will be able to write it as coefficients of x, coefficients of x squared, coefficients of y squared, and coefficients of xy, right? And ellipses are the same thing, just you dividing that by some constant. So it will be x divided by one constant plus x squared divided by one constant plus y squared divided by another constant equals some constant, okay? Same kind of equation. So it's kind of combination, linear combination of x squared, y squared, and constant, and xy also. Okay, depends on how that ellipsoid is prolongated in which direction. So all of them could be defined by that matrix, all of the shapes and forms, right? Circles, ellipsoids, all of that. And when you take matrices of higher order, you're practically generalizing the same idea of these quadratic shapes to higher dimensional shapes, cubic shapes, or some other shapes. So matrix, you can think about matrices in general also, and their quadratic forms as those higher dimensional shapes, all right? This is just generalization, as mathematicians like to do, to generalize different things. All right. So now we want to define positive definite and semi-definite properties of matrices. So matrix A is positive definite if its quadratic form is positive. Again, this is number, and it needs to be positive for all x's, which are not 0. For 0, it clearly will be 0, right? So if it is 0, then this expression is zero, vector of zeros. But in the case where x does not equal to zero vector, then this needs to be positive for the matrix A to be called positive definite. But how do you prove that? Like, do you want to go through all of this possible x's? You have infinite number of possible x's, right? You can check it for all possible x's. Sometimes you can, sometimes it's like too difficult, especially for higher orders. It's not 2 by 2. For 2 by 2, it's relatively easy. The idea is that you will write that as a function of x and y and their squares, okay? And you will try to complete that expression to overall square, okay? Completion of squares. Do you know what procedure of completion to square means? So you're trying to write some expression as square of some other expression, okay? And this is typically pretty complicated. If it is like x squared plus y squared, it's easy, right? It's just sum of positive numbers. But if it is sum of some other more complicated expressions with xy in it, it's kind of more difficult. I don't know if you learn quadratic equations that way by completion to squares, because solution, the formula for solving quadratic equations coming actually from completion to squares, quadratic polynomial. You're doing, instead of x squared plus bx plus c, you're doing x plus something squared plus constant, okay? And then like you express it in when it's solving quadratic equations. Yeah. We want them, you don't solve it over, you don't quadratic equations. But typically what we want to say is you have, let's say, x squared plus ax plus b, okay? If you want to solve the quadratic equation, just standard quadratic equation, and you find the formula how to solve the quadratic equation. You don't need to remember the formula. You can go in completion to squares, which will be practically you need to write it as x plus some sort of alpha squared plus some sort of beta. Okay. We need to find this coefficients alpha and beta from the expression by completion to some things. Okay. Now, what will happen is that this equation is very easy to solve, right? Because what happens is that x plus alpha squared will be minus beta, right? It is easy. The square root of z will be square root of z. It's especially convenient when beta is negative. Okay, so we don't need any complex numbers here. Okay, but even if it is complex numbers, we know how to handle them now, right? So it's not a big deal. Beta is positive. But then this thing cancels, and then we get x equals practically plus minus that thing. It will be minus alpha plus minus square root of minus beta. Okay, this will be your solution of the quadratic equation. The only thing is how you find alpha and beta from a and b. So they need to be function of a and b. Right, so completing that to square by saying that this thing will be practically x squared plus twice alpha x, right, plus alpha squared plus beta. Right? Now you know that this thing is a, this thing is b. Practically speaking, alpha is a divided by 2. And beta is, let's say, b minus alpha squared, which is a squared divided by 4. That's like that. I haven't made any calculation, so it's, but this is the idea, okay? I'm talking just about the idea of completion to squares. Any quadratic polynomial, you can use that procedure, and then you solve, and that will give you the actual formula of the quadratic equation. Okay, so this is proof for a quadratic equation formula. If you put these values in the formula, this minus a divided by 2 plus minus, remember the formula for quadratic equation? You should get the same formula. Okay. So this is the idea, same thing you have in this matrix that we are talking about. You have quadratic form, which is giving you the quadratic polynomial of some kind. And then you need to identify if your completion to square gives you sum of two positive things, something squared plus something positive. So if, for example, beta is positive and alpha squared is also, I mean, that thing that you have, like x plus alpha squared is always positive, right? So if beta is positive, then that entire thing is positive. And this is how you do that. But it's still too complicated, right? It's like, well, you need to write, first of all, that expression of x transpose a x, then you get to some quadratic polynomial, and in higher orders, it will be a big nightmare because you will have polynomial of much higher order, and then you need to show that this polynomial is positive somehow. But for quadratic polynomials, you can just that kind of procedure, and you'll see if beta is positive, then the entire thing is positive. That's it. This is how you know. So a few simple examples. If A equals to I matrix, identity matrix, then quadratic form is x squared plus y squared. Very simple, obviously positive definite matrix. If this is diagonal of 1 and minus 1, which means like 1, 0, 0, minus 1, then you get x squared minus y squared, and clearly not for all x and y, this thing is positive, okay? It depends on x and y, so it's not positive definite, it's indefinite matrix. Now, semi-definite is defined very similarly, but instead of larger than 0, you have larger or equal to 0. So it could be 0 at some other points except x equals to 0. It could be 0 in multiple different points, all right? So why all of that is important? Because technically, when you're thinking about positive definite matrices, they define some sort of cost function which looks like a ball in n-dimensional space. Again, I'm giving you three-dimensional expression, like parabolic in two-dimensional space. It has single minima point. And this is great for optimization. And it's called also convex optimization, which is using a lot of that type of tools because you have function which has single minima. So if you're using gradient descent or using some other tool, you will always converge to the global minima and not local minima, as all kind of other functions will give you, which is big deal in optimization. You want your problems to be convex, and you want your problems to have positive definiteness of some kind, because these matrices are very easy to work with, and they have single minima in that function x transpose ax. And this is why many people actually define cost functions as x transpose ax with positive definite matrix A, if possible. Again, depends on your problem, but this is where we want to go with it. Okay, we want it to be positive definite. It's nicely behaving type of matrices, especially for optimization. And indefinite ones will look like that, so you might have like different inflection points and so on, which are much more difficult to deal with when you have especially n-dimensional function, which you have no idea how to deal with. This is the problem. But we have also much easier method to identify if particular matrix is positive definite or not. And here is the method. Completely equivalent to finding that x transpose ax larger than 0. You can just look at the eigenvalues of that matrix. If all eigenvalues are positive, then this matrix is positive definite. If you have also 0 eigenvalues and the rest are positive, then it's semi-definite, positive semi-definite. And similarly, you can define also negative definite and negative semi-definite. So negative definite will mean that all of the eigenvalues are negative, and semi-definite will mean that all of the eigenvalues non-positive, which means you might have some zeros in it. Okay, so this will be semi-definite. It might be multiple zeros, eigenvalues, and most others are just negative. Okay, so this is negative definite. Now, you have even simpler test for symmetric matrices, which is called Sylvester criterion. Have you heard about Sylvester criterion? Okay, and again, when I'm saying simpler, I'm saying simpler by hand, not necessarily by computer, because Sylvester criterion is using determinants to identify positive definiteness. So you can estimate it very fast when you have like matrix 3 by 3, but it would be like pretty complicated if you have like matrix 1 million by 1 million, because you will need to compute determinant of that matrix. So here's how it works. If all of the principal minors of the matrix are positive, then the matrix is positive definite. So what are these principal minors? So principal minors, these are determinants which are sitting on the main diagonal. So you're taking, first of all, A11 element. It needs to be positive, okay? Then you're taking determinant of the first 2 by 2 matrix, sub-matrix of your overall A matrix, okay? In the upper left corner of the matrix, making determinant of that thing. Then a little bit bigger determinant, and bigger determinant, and bigger determinant. If all of these determinants are positive, your matrix is positive definite, okay? You're just going from the left upper corner, 1, 2 by 2, 3 by 3, 4 by 4, all of these determinants should be positive. And then the matrix is positive definite. Again, for smaller matrices, works great. For bigger matrices, computationally expensive, you know? So this is another criterion. And so, for example, this matrix that we talked about, both eigenvalues are positive, so this matrix is positive definite. And as you can see, this property of definiteness is spectral property related to eigenvalues by definition practically. And you can prove that this relation holds true always, okay? I'm not proving it, but you can go to linear algebra books which are talking about that and see the proof if you're interested. Any questions on that? So this is about positive definite matrices, and we will need positive definite matrices for multiple different purposes. And you have many, many different applications of this positive definite matrices in engineering as well. So one, as I mentioned already, optimization, convex optimization, you designing some convex function, and you have unique minimum because your cost function will look like that, more or less, but in n dimensions. So you still will have some global minima, and the surface will be convex. Do you know what convex means? Ball-like shape, but more formally, how do you define convex functions? Well, downwards, it's when you have like 2 or 3 dimensions, like how that would work with bigger number of dimensions. There is no up and down in other dimensions, right? It's like not well defined. So technically speaking, convex function, if you're thinking about like filling some space, okay? The line which is connecting any 2 points on the convex surface should be inside of the surface, okay? This is how it technically defined. Like the set of all of the convex points need to include all of the straight lines connecting any pairs of points inside of that volume somehow in n dimensions. And you can show that mathematically as well. You can expand that to any number of dimensions, that type of definition. Again, we will not do that. This is just convex geometry, but this is the idea. All right, so you use that in Lyapunov stability, where you have Lyapunov functions which look like x transpose px, magic, same quadratic form, okay? And P will be positive definite matrix in that case. You use it in covariance matrices, power spectrum analysis, in all kind of biomedical signals, if you're interested in biomedical signals. And it's used also in image processing for energy and smoothness terms, optimization problems, where you have a lot of computer vision optimization problems. It's used also in neural networks. It's used in multiple different things. So it's having a lot of different applications. And it's weird why mathematicians do not teach it in linear algebra courses, because this is relatively simple. Just you learn about eigenvalues already. So if all of them are positive, then it's positive definite. All right. So something which takes me back to my early research years, image distances. One of my first publications on computer vision, where I actually use positive definite matrices. So I will give you that as example of application for positive definite matrices. And maybe it will be useful for you if you are doing any kind of image processing, image analysis, things of that kind, where you need to find, or convolutional neural networks, whatever. You want to find distances between 2 patches, 2 images. So you have 2 images, let's call them X and Y. you can think about image as matrix. Let's say not color image, like regular image, intensity, just gray level. Numbers from 0 to 255, like 0 is black color, 255 is white color, and everything in between, all kind of shades of gray, right? So it has that matrix of numbers, which is image patch, describing what you see in the image. And you want to find what is the distance between these two images. So the most simple one is just Euclidean distance point by point. You're taking pixel by pixel, doing distance, and then Euclidean distance between them will be square root of the distance between xi and yi, where x is pixel in image x and y is image y. Okay, so pixel by pixel, subtracting them, square root of the sum will give you Euclidean distance between two patches. Is it clear what we are doing here? Just comparing. This distance will be 0 if this is exactly the same patch, because all pixels will be equal. And this distance will grow as the images will become more and more different from each other. All right, so far, this is Euclidean distance. Now, another one is normalized cross correlation, very popular distance, much better in multiple different ways than Euclidean distance. And this one will be defined as just multiplication pixel by pixel, like each pixel you multiply by its own pixel from the other picture, okay? Summing all of the multiplications, which will give you practically correlation measure, right? Multiplication, like you're multiplying practically dot between two vectors. When you're thinking about image as long vector, parsing that into a long vector, it's just dot product between them, all right? And then you're dividing that by sum of the xi squares and sum of the yi squared, which is kind of sigma, standard deviation of each of the vectors. So you're normalizing it by, and that's why it's normalized, okay, you're normalizing it by standard deviation of each one of these vectors, practically speaking. Why is that important? Because what happens is you might get very, very high correlation just because one of the vectors is super high, like super high values in that vector, okay? It's not because it's similar to another vector. You want similarity metric of some kind, right? You want like to see like how similar some vector is. But if they are not close to unity vectors, unit vectors, one vector might be like super big in terms of magnitude, right? And if you multiply point by point, all of these big numbers like 255 times even 1, 2, 3, 4, 5, whatever, the sum will be huge, okay? It does not mean that they are highly correlated. It just means that one of the vectors is very big. So it's not great for comparison of two patches, two images. You need to normalize them somehow to make them kind of unit vectors. This is not exactly unit vector. You're not dividing by norm of x and norm of y. You can, it's possible to normalize them to size 1, and then you'll have even better thing. But in that case, NCC tells you normalize it by sigma. What does normalization by sigma means? Like if you had some distribution, like Gaussian distribution of values, this is normalizing by sigma. What does it mean? So your distribution, if it was normally distributed before, mostly like 65% of your values will be between -1 and 1, okay? After you normalize by sigma. Why? Because 65, I believe 65 or 66% of data in Gaussian is included around the mean. And then I believe 95% within 2 sigma distance and 99 point something within 3 sigma, something like that. Remember a little bit from statistical distributions. So most of the data included within this 3 sigma, regardless of what your initial vector was. Okay, so if you divided it by sigma, you already squeezed it between these n sigmas, all of the data. All of your data will be within -3 to +3, 99% of the data. All right? If it was normally distributed. Not always it's normally distributed, obviously, but this is just mathematical intuition behind what it does to the data. It squeezes the data to standard size, standard spread kind of thing, okay? So when you're doing that one divided by that one and that one divided by that one, you have normalized x and normalized y. And then you have correlation, which will be some number. If it is like very big number, this means they are very correlated. If it is very small numbers, they are not very correlated. So it's not exactly distance. For distance, you need to invert that relation. So maybe we'll be doing 1 divided by 1 plus that number, or exponent of minus that number, things of that kind. To get distance, like the distance will be 0 when they're super close and bigger when they are very far away. But you don't have to use distances, you just need some similarity metric, like how similar they are, and they will become more similar, higher NCC is. All right? Now this is not enough, and people invented zero mean NCC. And unfortunately, sometimes in many actually textbooks, they still call it NCC. They do not differentiate between the two because they never actually use that one. They always use this one. So do you recognize that formula? So what is that formula? It looks very complicated, but I'm pretty sure you saw that formula before, not in this course, in other places. It's Pearson correlation, the correlation coefficient. It's just what people call correlation, which is normalized between -1 and 1. Okay, so this is Pearson correlation, and this is Pearson coefficient or correlation, whatever you call it. Okay, so this is used to identify, especially in tracking. This is very popular in visual tracking, where you need to track particular object. It highlights where is the highest correlation. When correlation is very close to 1, the page looks very similar to the original page. When it's around 0, there is no correlation. This is not a good match. When it's -1, it's anti-correlation. So whatever looks black looks white in the other page, and other way around. Okay, so it's like opposite relation between pixels. It's like negative of the picture kind of thing. Any questions on that? These are the most, like 3 most popular techniques for comparing 2 pages or for tracking some objects and so on. You're just scanning the picture with these distances or with these correlations and finding the best match in the picture. And this is where your object is. Okay, finding point of maximal correlation or minimal distance. Questions? Yes. So image patch means just small image, small part of the image. Let's say you are tracking particular pedestrian in image sequence where you have all kind of things. So you're taking that patch and patch under it, and you're comparing these 2 pages, they need to be of the same size. Dimensions of the matrices should be the same. Okay? It's like 100 by 100 image. So think about patch as image. Just typically you're not using like entire image comparing to entire image. You're comparing some sub-image to some other sub-image. This is more practical. Okay, so some time ago, there was development in the distances of images, and there was proposed new Euclidean image for images specifically. The idea was very simple, actually. The idea was that images, if you're taking natural images of any kind, and you're taking particular point, particular pixel on that image, pixels nearby are very correlated to that point because the image has kind of smooth transitions from one object to another object. So if particular point is particular level of gray, you can easily assume that its neighbors will be of very similar gray level, okay? Unless this is just white noise where pixels are just jumping all over the place completely randomly, okay? So for natural images, all of the neighborhoods are correlated within themselves. The pixels have very similar intensity nearby. And the idea was that, well, correlation by itself is very sensitive to noise. Why? Because if you have noise in one of the pixels, it will give you big distance between the pixels, or bad correlation between these pixels, because you're doing that pixel by pixel. So if images are noisy, if patches are noisy, this will not work well, right? And this is what we see in practice. It's not really working well, okay? So the idea is that since I know that neighbors should be very similar, why not to use also to include neighbors in the calculation of the distance for that particular point, okay? So I will not only compute point by point, but I will compute neighborhood by neighborhood instead, okay? Which will make it much more robust to noise in the image. This was the idea, the overall idea of something which was called image Euclidean distance, okay? IMED, very interesting name. And the idea was that instead of using just Euclidean distance like that, which was just sum of all of the pixels squared and square root on that, you're still using square root, which gives you Euclidean distance, but now you're using that one in neighborhoods. So it's not xi minus yi squared anymore. It's xi minus yi times xj minus yj. And I might be different from j. Now, this will include all of the possible pairwise pixels, which is computationally super expensive, okay, especially for bigger images. But what happens is you don't need all of the pixels, really. You don't need like neighborhood of all pixels in the image. You need only locally something like which will be close to the pixel, because you don't care like what are the neighbors which are far away. So what was proposed here is to give weighted average distance, and weight will look, let's say, like Gaussian around that neighborhood, which means you'll give strong weights to neighbors which are very close and very weak or zero weight to neighbors which are far away, right? So for each pixel, you will do the Gaussian around it, and you will do that weight of Gaussian multiplied by that multiplication, which is regular correlation type of multiplication. So it will be squared times, let's say, 1 here, the weight of 1 for when this is the same pixel, like the maximum point, and a little bit less when you're going farther and farther away. So this function will depend on distance from your present pixel. All right. So this will be mn by mn matrix, huge matrix, okay? It will be symmetric, positive, definite matrix, because these distances are always positive or non-negative at least, okay? And the only distance, remember we learned about distances, what are the properties of distance function? It's always positive except one point. And this point is 0, when the distance is 0, where x equals to 0. This is the only point where any distance is 0, all right? So this is exactly that idea of positive definite matrix, all right? So what happens is that you can define that matrix using that Euclidean function as example, and many other positive definite functions, okay? But this is just one example. You're just computing negative distance between the point I and point j, which means that point that you're computing distance to and its neighbor j, whatever it is, and different neighbors will have different distances to that point, okay? And then you divide it by the coefficient sigma, is how broad you want that Gaussian to be, how many neighbors you want to include in your calculation, kind of question. And you compute that big matrix, multiply it here as a coefficient, and you get weighted sum which is much more robust to noise, which is a great thing. For example, if g equals to I, you get back Euclidean distance. Right, if this is identity matrix and you're not doing that, which means sigma practically is 0, it's like super narrow Gaussian, you get back your Euclidean distance, which means this is generalization of Euclidean distance, okay, for that particular case where g equals to I, matrix G. Any questions on that? Okay. Here is one interesting example. You have two matrices, which to our eye, these are images. So it's like white, black, and this is black, white, stripes, okay? Two stripes of white on black background or black on white background, whatever you choose, same thing in that case, all right? For our eyes, they will look completely same. It will look exactly the same. It's shifted by practically the same thing, shifted by 1 pixel. To the right, to the left, okay? So from our perspective, they are not that different, really. But if you compute in Euclidean distance between these two, it will be maximal possible distance that you could achieve. Why? Because like all of the 255s correspond to zeros and other way around. So it's like you cannot get bigger than that, assuming that the highest number is 255. That will be all of these numbers squared and then square root of their sum. Huge number, 1000 something. Okay, this is the Euclidean distance between these two images. Now, dz and cc, this is correlation, will be -1. They are anti-correlated naturally. Okay, not really similar. IMED will be 274. It's much better than this number. Still not ideal, but that's okay. I mean, you still have some shifts, so they are not the same. So you cannot say this is like zero distance between them. It's not zero distance, but it's kind of much more reasonable. Okay, it makes more sense that if we do not see much difference between these two images, they should not have maximal possible distance between them, right? And this is what IMED is doing for you. It's just giving you more reasonable number, okay, for that type of cases where neighbors matter as well. Any questions on that? All right. So generalized cross-correlation. This is where I started and started to expand that to more things. Because, well, Euclidean distance is great, but it's not normalized. It could have any values from 0 to infinity. Depends on the images, depends on the pixels, depends on, like, it's not scaled to anything. And it's even very difficult to imagine how you would scale that to anything useful, like how you normalize it. Because how you normalize Euclidean distance if you don't know what the images are? You can't really. So correlation is much easier to normalize, okay, because it's inverse relation. And it's easier to normalize. So what we have here is generalized cross-correlation. And I will write that as F transpose some matrix G times F of another vector Y, all right? So for some positive definite matrix G. So why is that generalization of all of the other correlations we talked about before? Because for NCC, if you choose G equals to I, you get practically F transpose of X times F of Y. This will work for F of X equals to that particular function. Okay, you'll get regular correlation for that function. There's one component times another component, dot product between them will give you that correlation. How about zero mean, same thing? So same thing, G equals to I, F equals to that function now. So subtracting mean first, and then you're dividing by sigma, all right? So this is still same kind of formula. And then my question became like, why should I use G equals to I? There is no reason in particular to use only correlations with G equals to I. This is a very specific matrix, but I can put any positive definite matrix here instead of I. And then I will have all of the neighbors included also in computation of the correlation, similar to IMED. So I generalized that from the same idea. I took these two ideas of generalized cross-correlation and IMED. I said, like, let's generalize correlations now instead of distances. So this is what I did. These are two distances that I published that I called image normalized cross-correlation and image zero mean normalized cross-correlation. Same formula like IMED, just this Gij, which is that weight, you're using for correlation now, and here you are using it for normalized cross-correlation now, okay? Same formula with Gij, just positive definite matrix of any kind. It could be Gaussian matrix, it could be whatever, right? So practically same idea. But now the question becomes, is it really normalized between -1 and 1, like Pearson coefficient, things of that kind, right? Because this is what I wanted it to be. Now, these formulas look very complicated because this is some coefficient weight times all kind of double sigma kind of things, okay? Like, how do you know that this thing is between -1 and +1? Like, can you prove that kind of thing? Can you, like, I tested that on multiple different images. It's getting me numbers which are in that range. So it gives hope that this works somehow, okay? But can you be sure? Like, how would you know? So it is true, and it is actually not very difficult to prove. So here's the proof. All right, if you know linear algebra. The idea is that practically speaking, that kind of thing is inner product. So for any positive definite G, X transpose GY is inner product. And the corresponding norm will be X transpose GX. So it will be norm. Now you have Cauchy-Schwarz theorem, which is stating that inner product squared absolute value is always smaller than X norm times Y norm. All right. So this is the theorem, Cauchy-Schwarz inequality. This is exactly that thing, all right? Like these formulas practically telling you exactly that Cauchy-Schwarz theorem. So if this one is true, and that inner product of X and Y is smaller or equal to norm of X squared, norm times norm of Y squared, you get exactly the same equations that I've got here, right? This equation, and this equation will be for the same thing when you shifting the variables by the mean, okay? So they still will be just different vectors. It doesn't matter if you shift vectors by a constant, okay? The constant is mean, you're shifting by that constant, you get another vector, but this is true for all vectors, X and Y, right? So it doesn't matter if I shifted them, multiplied them by constant, or did whatever with them. It's true for all vectors. So that proof took like 5 lines, right? For both of them, for both formulas. And then you get that nice relation that all of them are between -1 and 1. Any questions on that? And here are some nice properties. Let's say you shift your patch a little bit. What kind of property you would hope that distance or that correlation to have, similarity metric to have? So if you're shifting some patch a little bit, you don't want it to affect it too much, the distance, right, or similarity. It's still similar. When you move too much, it's already very not similar. How do you want it to look like? You want it probably to go linearly up. The distance should go linearly up somehow, okay? And this is what you actually get from different distances. So this is a Euclidean distance. Like if you move a little bit, it jumps a lot, okay? And then starts to be kind of linear until it gets to the maximal possible normalized distance, all right? Now, if you're taking NCC, normalized cross correlation, then it also jumps a lot and gets a little bit better in a sense, right? And this is why Euclidean distance is rarely used for patch comparison, and NCC is frequently used for patch comparison because it's just better, all right? But here is what my 2 proposed functions are doing. So they look like that red, which is almost linear. So it's going linear with distance, like farther you go away, farther this distance becomes, okay? And this is how IMED looks like. So it's very smooth, much more smooth than all other metrics, because it's not jumping a lot. It's moving smoothly because you have that kind of filtering built into that technique. Now, how about detecting targets? You have visual tracking, and I'm going fast through that. I'm not getting into details of that. The overall idea is you have some patch, and you want to detect that patch in the image, and you want to track that car or pedestrian or whatever it is. You want to track it in video sequence, okay? So you want that you're scanning the neighborhood where you're looking for your object, okay? Subject, object, depends. And then you are looking for maximal similarity point, right? This is where the centroid will be. This is where you want to put your patch. This is where you detect your object somewhere. So here was the experiment. I'm taking some patch from the image, taking some other image and trying to find that object in that image, scanning the image and finding all of the similarity points and finding maximal point and saying, is it true target? Like, have I got it right? Or have I got it wrong, right, in that image? Okay, and these are practically distances that I have for true targets and distances that I get for false targets, okay? When I do not match between the actual location. So what I want that thing to be practically as dark as possible, like minimal distance as possible. So I want it to be black, that rectangle, that true target rectangle, and that rectangle to be as bright as possible. Okay, I want the biggest distances to false targets, right? Because if target is incorrect, I don't want it to match well, right? So the idea is that that half of the image should be white and that half of the image ideally should be black, all right? And then I measure in different distances. This is Euclidean distance. They are not that different really, okay? This one is a little bit brighter, this is a little bit darker, not great, okay? This is IMED, which is kind of better. So this is a little bit brighter, but you still have a lot of like dark things here to false targets. So it detects false targets as correct targets many times, like false positives, all right? Now, IMNCC that I defined, it's not great for tracking in that case. It's much better for pattern matching, okay? You have some very bright lines here, and you clearly see that this is much darker than most of these lines. So it's already better than all of the what we saw before, but still not great. But look at zero mean one, okay? So this one is almost white and this one is almost black, which means it's as close, very close to ideal one, okay, for visual tracking. So if you're using this one, it will work pretty great at visual tracking of different patches, okay, in the images. It's also having all kind of other nice properties for distances related to rotation, noise sensitivity, and other things. So you can look at it, for example, that IMNCC is the least noise sensitive out of all of the possibilities that you have here. IMED is also very low noise sensitive, but that one that I propose for tracking is third best in terms of tracking. And it is even better than IMED at lower noise levels, all right? Which is having just great properties of distance. What is the actual problem of that? Like why nobody like really using that every day in all of the algorithms that people are using for image matching or recognition or neural networks, CNNs, and all of that stuff? What is the problem? Not problem, but why people do not use it? So it shows all these great properties. Robust to noise, tracking very well, and so on. Why not to use it? 2 points. Why it's not working? First of all, people don't know about it. This is easy one. Second one, it's computationally much more expensive. And all of the neural networks, convolutional neural networks, and all of the other modern algorithms already at the maximum of their abilities in terms of computational power, even with the most simplistic convolution operation between two patches, okay? Because right now you're comparing it using just convolution or correlation. So it's like basic correlation, not even normalized, regular correlation for CNN networks, all right? It's already taking too much memory, too much energy, too much of everything in GPU power. If you add that thing, it will be even slower. Okay, we don't have enough computer power, but eventually we will, okay? And then you need to be ready for these algorithms to shoot up. Okay, moving to Lyapunov stability. Any questions on the previous one, on that part? Okay, another example, yes. For smaller sets, yes. I have 2 students working on that, yes. Okay, Lyapunov stability. So Alexander Lyapunov, very interesting person, is tragic end. And he was very famous at his time, one of the first developers of stability theory in general. People just started to develop stability and what it would mean for dynamical systems in general. And he proposed something which was extraordinary and very forward-looking, I would say, unexpected, because at that time, people worked with transfer functions. They tried how stable particular polynomials are. At that time, the best they could do polynomial of third order. This is all they could do. So you had Rawls-Hurwitz criterion. You had actually interesting persons that you might know by name Maxwell equations for electrical engineers. So he was one of the fathers of stability theory. Nobody knows him for that, but he was the person who published paper on governors, which were the name of controllers at that time. Okay, it was 1890s probably, or 80s, more than 100 years ago. And then nothing really was known on how to identify stability of the systems in general. And Lyapunov proposed very generic theory, how you identify stability of any systems, including nonlinear systems. Like people just started to talk what transfer function is, okay? At that time, what polynomial type of representation, linear system. He started already with nonlinear systems, which was like very forward-looking, okay? 100 years forward-looking. And he developed his theory for any kind of state space systems, including nonlinear ones. And stability is defined by him, which is not standard stability that we typically learn like controls courses like asymptotic stability or Bibo stability, but it's very similar type of stability to regular types of stabilities that we're familiar with, okay? And he had, as I said, very tragic end. His wife was very sick with tuberculosis. And at that time, obviously no antibiotics, no treatment, no vaccinations, no nothing. The only treatment was like to go to south, and doctors recommended his wife to go south to Black Sea. And they went to live in Odessa, by the way, a very beautiful city, built by the same architects who built Paris and Rome. Just interesting fact. So they went there and she passed away, unfortunately, still in Odessa, and he committed suicide the same day. Yeah, this is his tragic end. He was relatively young. Okay, so back to the control systems. This is kind of to the point, like mathematicians are very sensitive people, try not to hurt them, okay? All right, so we are talking about stability now. And motivation for the definition of stability, because we have multiple types of stability, and this is just another type of different kind, very important one, but kind of different from what you saw before. If you took any controls courses before, if you never took controls courses, you can skip through most of that material. Doesn't matter that much, it's just example of applications of positive different matrices. So I'll skip fast through that, and you'll have also project presentation on that topic, so I don't want to get too much into details. But you have two typical types of stability. Bibo stability, which is bounded input, bounded output, which means that if your inputs are bounded, not infinite, your output should be also bounded, okay? Also not infinite, not diverging anyhow. This system is Bibo stable. If for any bounded input you get bounded output, it's Bibo stable system, okay? Asymptotic stability is kind of very strong. It means that you will converge from any possible initial conditions, your system will converge to zero, always. All right, this is asymptotic stability. It's very strong stability, too demanding for most systems. You can imagine many different systems which are kind of stable, but they will not converge to zero. Let's say card, okay, you're putting it on the table. Is it stable? It's not at 0 point, it's just somewhere on the table, okay? You would define that as stable, but it's not asymptotically stable, okay? Even if it is standing and not moving anywhere and not running away, okay? So for that type of systems, Lyapunov defined Lyapunov stability. So systems which are not running away, or the energy, additional energy is not introduced into the system to run it away from your initial realm somehow, okay? So this was the overall idea of Lyapunov. So here is mathematical definition of all kind of internal stabilities, continuum time, Lyapunov stability, and probably I shouldn't go into the formal definition with epsilon delta type of calculus definitions. This is textbook definition. Here is the intuition behind it, okay? You have state space system of some kind, and you can provide that state space system with all kind of initial conditions. From initial conditions, it will start dynamically to do something, or maybe it will not do anything. Maybe it will stay with it, whatever you put it in, like that card on the table, it will stay forever in that position, okay? So asymptotic stability means that if you disturb it a little bit, it has to return to 0 point. But for Lyapunov stability, it doesn't have to be. What has to happen, if you're thinking about trajectory of this axis in phase space, which means coordinates of the vector x1, x2, x3, and so on, you have that state vector, okay? This vector will not leave some bigger radius if you're starting with a smaller radius. So what happens is, if you choose any initial conditions within that initial smaller radius, okay, it will move somehow, it will do some trajectory as a function of time forever, okay, or it will stay at that point or whatever, right? So it will do something based on that iteration of next x equals to a times previous x, okay, state space equation, all right, from this initial conditions, which is x0. And this point could be in n-dimensional space. Here it's like 2-dimensional space, but could be any dimensional space in a sense. And what happens is it will kind of do all kinds of things inside. It will never leave the bigger circle. And from my perspective, this is how you think about that. Give me circle of any radius, okay? Or sphere of any radius in 3 dimensions, or hypersphere in n dimensions. Okay, give me the radius, which will be that R, big R, capital R. I will always be able to find smaller r within it, such that no matter where I start inside of that smaller ball or hypersphere inside, my trajectory will never leave your radius. So for any bigger r, I will be able to find smaller r. Okay, then the system is Lyapunov stable. Okay, this is the overall idea of Lyapunov stable. So yeah, it's a little bit complicated. It's very generic, but you have all kinds of properties how to show that system is Lyapunov stable instead of going through definition, because like doing that by definition, almost impossible to prove that system is stable or unstable in terms of Lyapunov. But this is a definition, okay? This is how Lyapunov defined that thing. And I have, by the way, his original thesis, a copy of his original thesis. Very interesting work. It's pretty long, very mathematical. And then when I started to read it, it was like, come on, like nobody can understand that. There is no way that anyone actually understood that kind of stuff. Because he says like, well, this is obviously known to everyone that this theorem is stating such and such, and it has very elegant proof by such and such. I'm saying like, I never heard of it, okay? It's like after like 10 years in that field, never heard of it. And he says like, everyone knows it. You know, it's like frequently you have in the text, he says like, it's very well known, such, blah, blah, blah. No idea. So his thesis is very high level math. And I don't know if his mentors knew all of these things. Probably, I don't know. People were smarter 100 years ago. I don't know any of it. So it took me a while to get even through. I never got it to the half. I got through the first quarter probably with a lot of help from textbooks and other sources. It was tough. Okay, so it's very difficult to apply that type of definitions and to understand what it even means, but that's okay. I have an entire course on that now. Again, modern control next semester, if you're interested, we can talk about details of that thing and how you actually do that. All right, so how do you identify stability of particular equilibrium point of your linear or non-linear system? For linear system, it will always be 0 point. For non-linear system, it might be some other equilibrium point for which you can identify stability. You need to define something which is called Lyapunov energy function. And again, this is pretty difficult in the first place. But this function of a vector x, of a vector state vector, and this function will be scalar function, and it will have all kinds of properties. So it's defined by its properties. Again, mathematicians love to define functions by properties and not explicitly, because there is no explicit definition. I saw people complete entire doctorate on designing Lyapunov function for a particular plant. Okay, you have that kind of thing. This is that difficult to find that kind of functions. So the properties that they have is that this function should be a continuous function with continuous partial derivatives with respect to all state variables, which means dv to dx variables. And for all x not equal to 0, it needs to be positive. V at 0 should be 0. So again, think about that Bowl function, okay? And derivative should be negative for all x's in neighborhood of the origin, which means it's kind of global point, global extrema point, right? So this is a function. Then you can compute that using particular simplifications. We can skip through all of that. So here are the stability theorems of Lyapunov. First of all, equilibrium point is Lyapunov stable in particular neighborhood in that hypersphere, whatever it is, of radius epsilon, if this function exists. Again, can you apply that practically? Well, if you can guess that function, then yes, but it's doctorate takes a PhD to design that function, okay, for a particular linear or non-linear system, okay? For linear, we know the answer. For non-linear, each system is different V function. But again, as you can see, it's generic for any non-linear system, okay? Give me the system, if I can guess that function, which works for that system and having these properties that I listed before, it will be Lyapunov stable, okay? System will not diverge, no new energy will not be introduced into that system. It will not run away, right? Now, more than that, it will be asymptotically stable if this is strictly less than 0. So in that definition, it was less or equal to 0. But if you replace that with less than 0, then it's also asymptotically stable. Again, linear or nonlinear doesn't matter. If you get that function, works for everything. If the equilibrium point is not 0, you can just shift it and get new state space equations and do exactly the same theorem for any equilibrium point. So it works for any point practically in space, just by shifting it. Again, I'm not getting into details, but here's what we have for linear systems. For linear systems, we have explicit functions, Lyapunov functions, and this is why we learned about positive definite matrices in general. So what happens is LTI, linear time invariant system, is globally asymptotic, and this is continuous time system, like x dot equals ax, state space system, with matrix A and vector x, is globally asymptotically stable if and only if all of the eigenvalues is smaller than 0. That's what you learn in control systems course. So all of the eigenvalues need to be in the left semiplane for the system to be stable. For discrete systems, the same thing, saying that it needs to be in unit circle. All of the eigenvalues of the state space need to be in unit circle. Again, I'm not proving it right now. I'm just stating that this is eigenvalues are poles of the system, and then poles need to be in the left semiplane for continuous time systems or in unit circle for discrete time systems, okay? But here is Lyapunov approach to having a asymptotically stable system. You solve that matrix equation, okay, with matrices A, and this is your matrix A, matrix P, which is symmetrical matrix P that you want to find. So this is what you want to find. And this is matrix negative I, all right? You can just replace Q with I, identity matrix. It could be any other positive definite matrix, okay? Just pick any positive definite matrix. It would work same way for all of them. the system will be asymptotically stable, that linear LTI system, asymptotically stable, if P is positive definite, which is interesting relation, right? It's like, where is it coming from? It's completely unconnected to all of the eigenvalues, it's completely different, right? But this is a theorem. This is Lyapunov equation, which is saying if you're solving that Lyapunov equation and you get P, which is positive definite, the system is asymptotically stable. And this equation, Lyapunov equations for discrete time systems. If you put here I and you compute P, and pay attention that this is linear system of equations. Why? Because it's like all linear combinations of coefficients in the matrix P. Okay, so it's like system of linear equations practically, and n equations. So if you solve that equation and you get P positive definite, then you get asymptotically stable system. All right, so you're just choosing Q equals to I, and here is the standard Lyapunov function for all LTI systems. That solution of that equation is a positive definite matrix which works for you, gives you that Lyapunov function, and you can check that all the properties of that function, which is hopefully now you recognize as quadratic form of the matrix P, positive definite matrix P, and symmetrical, is Lyapunov function. This is the actual relation, okay? I don't think that we have time for solving that equation. I can, if you're interested, I can send you solution for that particular equation, but it's very easy. You just put matrix here, matrix there, and you're solving for P, you get all kind of values of P, checking that it's positive definite, all of the eigenvalues are positive, and that's it. I can send you the solution. Any questions? All right, thank you.